Hey, what's up everybody? I'm going to be talking about a sad topic, and that is getting in accidents. Nobody wants to get into an accident. When you get into an accident, you got to pay a lot of money. Here are the different costs for how much people paid when they got into a little collision. $3,345, $743, $663. This is 10 collisions, and this is how much they paid. Now, what we're going to be doing in this video is trying to estimate how much does a collision cost for the whole population. This is just 10 vehicles, but we want to know, can we use this data to estimate how much do we think a collision will cost for these types of vehicles? Alright, so we're going to be doing that. Confidence intervals for the mean. And we're also going to be talking about a cool program called Statrcrunch. So let's get to it. So first of all, it says the data shown below represent the repair costs for a low impact collision in a simple random sample of mini and micro vehicles. So here's all of the data. Now, one thing to notice is that this data set is pretty small. So we're going to be modeling this with a t-distribution because we don't know sigma, the population standard deviation. But in order to meet the criteria to use a t-distribution, either the sample size is greater than or equal to 30, or it's normally distributed. This data right here is normal. Those are the two conditions. So we know that the sample size is, what, 10? We got 10 data values there. So that's not greater than or equal to 30. So we need this data to have come from a normal distribution, but it does not say that. So we're going to check this data to see if it came from a normal distribution. Okay, so this is the problem in my math lab. We're about to go into Statrcrunch, a really cool program that does a lot of great stuff. So what are we doing here? We're trying to do the following. So this is the 10 data values for the collision costs. So check out the problem. We're going to draw a normal probability plot to determine if it is reasonable to conclude that the data came from a population that is normally distributed. So we're going to be looking for the data to conform to a line, kind of like these graphs here. All right. So now remember, we got the cost of the collisions for mini and micro vehicles. So look at this box right here. This is how you get to Statrcrunch. We click this box here and it takes us in to Statrcrunch. Just open it up and there's the data. It pulls in the data for us. We go into graph and QQ plot. We click variable 1, click these buttons here, press compute, and there it is. So look at that. There's the points. We have this strong correlation coefficient, 0.967. In fact, the strongest that it could be is 1. So this is pretty darn strong. Now, so let's take a look. Let's experiment a little bit. Let's plug in some data that is skewed right. I'm going to try to plug in data that is not normal, right? So let's imagine a skewed right distribution with a bunch of small values like near 3s, like in the single digits. Like the majority of the values are pretty small. Then let's start putting in a few values that are really big. So like shorter tail to the right, a longer tail to the right. It's going to be skewed right. For example, what kind of values can we plug in here? Let's plug in like 200 and 400. Imagine these are like incomes, right? Incomes are like skewed right. Most people make lower amounts of money, and then you got all these couple of millionaires and billionaires over there. All right, so this data is skewed right. So it should not come from a normal distribution. So if we use this data, we come in here and we change this to variable 3, press compute, and now check it out. Look at our correlation coefficient. Wow, it's so much lower. Look at this. Look at how this looks. It doesn't seem to conform to a line very well. It's only 0.545. That's the strength of the correlation. It's very low. The closer that is to 1, the stronger the correlation. And you can see, since it's skewed right, it's telling us that this is not from a normal distribution, which is great because it's not. I designed this data, I plugged it in to be skewed right. So this works beautifully. This QQ plot, this normal probability plot, it is able to tell whether or not data come from a normal distribution. How amazing is that? See, this data, it was from a normal distribution because the correlation coefficient was stronger, but this data is not. So the correlation coefficient is weaker. This is linear regression. The normal probability plot conforms to a line and it has a strong correlation. I want to show you how to find box plots. You go to graph, hit box plots, click both of the data sets in variable 1 and variable 3. You can draw them horizontally, press compute, and look, we got the box plots here. Now, look, this is an outlier, so this top box plot looks really weird, and this is kind of crunched up. Because of that big old value over there, that 40,000, it's kind of making this box plots look really weird because the data is so wide, the range is so wide because of the 40,000. And all these dots are basically outliers. If I get rid of the 40,000 and then redo the graph by just going to edit and just press compute, look, it looks a little bit better. There's 3 outliers on the top, and look at the correlation coefficient. It's still 0.454, which is very low. If I redo that, now actually, sorry, I redo it, now it's 0.61, it got bigger, see? And that's because, hey, this thing is skewed right. This top graph has all these outliers on the right, and it does not look normal at all. So that's why this graph doesn't conform to a line. So this stuff works, man. It's detecting that it's not normally distributed. So yeah, just remember QQ plot. That's how you check for the normal distribution. You can even do them both at the same time. If you click these, go to compute, it does them both. So you just got to click to the right. The first one's 0.967 and the second one's 0.61. So if you want to do them both at the same time, you can do it like that on Statrcrunch. So this is an amazing program. Okay, so now we can reasonably assume that this data came from a normal distribution. So let's start the problem. Look, we're trying to make a confidence interval. So we need a point estimate of x bar, and we need to find the margin of error. Once again, we only are going to have s, but the 2 things we need are, what 2 things? X bar and s. We call those our summary statistics. We find those on the calculator. We have to plug this data into a calculator like this. Here's the data. You go to stat, edit, and look, the data is all here in L1. I already plugged it in. So I'm going to find the summary statistics. How do I do that? I go to stat, and I go to calc. 1 var stats, plug in second 1, and there you have it. So that's our mean and our sample standard deviation. You see them, 1758 and 1007. So let's write these down. We got x bar equals to 1758.4 and s 1007.02. So now we have our summary statistics. So let's see what we're going to do here. Construct and interpret a 95% confidence interval for the population mean cost of repair. So here's the confidence interval. We've got the point estimate already, and now we need to find the margin of error. Okay, a margin of error has S, T star, and N. Well, we already have S and N. What's N? N is 10, so we can write that down somewhere. That's N equals 10. So the only thing we need to find here is T star, that's it. The way you find T star is like this. This is a picture of how you find T star. It's a 95% confidence interval, so the shaded region in the middle is 95%. So these 2 critical values contain 95% of the data. So how do you find this critical value? Well, one of these critical values. Well, if 95% is in the center, if you do this little calculation down here, you find that the tails contain 1 minus 0.95, which is 0.05, but there's 2 tails, one on the left and one on the right, so I have to divide by 2. So I get 0.025, so I can say that in here is 0.025, and same thing in here is 0.025. So now I just need to find one of those critical values using inverse t. So let's see, we can find either one of them. We can find the one on the right if we want by saying inverse t, and the area to the left of this value is actually this area plus this area. So this is 95 and this is 2.5, so that's 97.5, so 0.975. If you want, you can do it that way, or you can just find the negative t star and just plug in 0.025. That's sometimes easier. So we can plug in the degrees of freedom, which is 9, and 9 is 10, so the degrees of freedom equal 10 minus 1. That's how we get that 9. So this is going to be what? We got to use our calculator now. Come over here. Let's see, what do we get? Let's see, second distribution, inverse t, 0.975, comma 9. So we get 2.2622 if you round, 22. All right, that's our critical value. Okay, So we have everything to find the margin of error. So that's the next step. Now find the margin of error. So we're going to get that this equals to, let's see, what did we have for T star again? 2.2622 times S, which was, we have it there, 1007.02. We could even say 0.23 divided by square root of 10. So that's how we find our margin of error. See that? Just plugging into this formula gives us the margin of error. What do we get? Times, just take that previous answer. I could do a fraction here. 1007.023 divided by square root 10, and that will be your margin of error. So it is 720.381. Okay, so that was the second step. We found the margin of error. Okay, now what? Lastly, find the confidence interval. Okay, so this is just a picture of the summary statistics right there from the calculator. So we're gonna find the lower and upper bound of the confidence interval. This right here is the lower bound, and then this right here is the upper bound. So we're gonna say that the lower bound is, what's X bar again? 1758.4, and then 1758.4. So this would be minus the margin of error plus the margin of error. What was the margin of error? 720.381. We'll just round to the tenths place. Let's see, 1758.4 minus 720.4. And then I'm going to take this, enter, and then change the subtraction to a plus sign. So I get the lower bound is 1038, upper bound 2478.8. There's your confidence interval, lower bound and upper bound. And that's it. That's how you find the confidence interval for the mean using the t-distribution. Let's see. If you want to interpret that, you could say we're 95% confident that the mean repair cost is between 1038 and 2478.8. That would be your interpretation. So make sure you say we're 95% confident. Okay. All right, let's check out one last little question. Suppose you obtain a simple random sample, size n equals 10, of a specific type of mini vehicle that was in a low impact collision, and determine the cost of repair. Do you think that a 95% confidence interval would be wider or narrower? Explain. The thing about this one is that we're dealing with a specific type of mini vehicle, so we're going to say that that we're dealing with like less variability here because we only have one type of vehicle. It's only a mini vehicle. And in the last questions, if I scroll up, it said that we had mini and micro vehicles, so there were two types of vehicles. So there's like more variability, different types of cars, but this is like one specific type of car. So there's less variability, so we could say less variability since it's only one type of vehicle. So more narrow. All right, so we're gonna say that there's less variability since it's only one type of vehicle, and that's gonna make the confidence interval is gonna be more narrow. All right, hope that helps.